Welcome to Study Loop.
This is the answer to Chapter 21, problem number 80 from the Smith Organic Chemistry textbook. And this problem says, although the carbonyl absorption of cyclic ketones generally shifts to a higher wave number with decreasing ring size, the C double bond O of cyclopropanone absorbs at a lower wave number in its IR spectrum than the corresponding bond of cyclohexanone. And explain this observation by using the principles of aromaticity learned in Chapter 17. Okay, and so the first thing to do here is going to be to draw each molecule and to draw its resonance structures. So cyclopropanone is there, and it's going to have 3 resonance structures. So the first one we can make by, instead of drawing a double bond here, drawing it as the charge separated version. So a single bond. And then our other 2 resonance structures are going to result from basically just moving the double bond and the charge around the 3-membered ring. So we can put, sorry, this is probably a little too small to be easily seen. So let me draw it a little bigger. So we can put the double bond there. We'll still have just a single bond here, 3 lone pairs on the oxygen and a negative charge. And our positive charge will now be at that corner of the 3-membered ring. And then the final resonance structure to consider here is going to result just from movement of the double bond to the other possible position. And so also movement of the positive charge. So then the positive charge will be up on this carbon, and there will still be this negative charge here. Okay, and so we can contrast that with cyclohexanone. And I will draw it with the same orientation here. Okay, so there's our cyclohexanone. And we can draw, so in exactly the same way, we can draw a resonance structure where instead of the double bond between the carbon and oxygen, we're just going to do the charge separated version. So there's the charge separated version. And then again, we can move the double bond and the charge. Oh, God. There we go. Okay, so if we were to put the double bond there, obviously that changes nothing in terms of the oxygen, but it would put our positive charge on that carbon instead. Okay, and so when we're looking at these 2 molecules and their 2 sets of resonance structures, what we see is these resonance structures here are all aromatic. And so since they're aromatic, they're much more highly stable than we would expect. And so they're going to contribute a great amount to what the overall structure of this molecule is. So what that means is that this molecule exists as a hybrid of these 4 structures, but these 3 aromatic structures contribute to a great degree how the molecule is actually existing. And so what that means is the carbon-oxygen bond, rather than having a lot of double bond character, has a good deal of single bond character. Because in 3 of these 4 resonance structures, it exists as a single bond. And again, those 3 resonance structures contribute quite a bit because they're aromatic. So there is a good deal of single bond character in that carbon-oxygen bond in cyclopropanone. In cyclohexanone, there's no aromaticity. So none of these resonance structures, well, no, let me not say that. So the first structure is probably the most stable because, of course, charge separation. So these second 2 structures with charge separation make for less stable structures. So the first structure probably contributes by far the majority to how this molecule exists. And so there is a good deal of double bond character between the carbon and the oxygen. And so for cyclopropanone, the high degree of single bond character means that the IR spectrum of that molecule, the carbon-oxygen bond, is going to look much more like a single bond than a double bond, and so is going to have a much lower wave number. Yeah, but for cyclohexanone, the carbon-oxygen bond it is basically a carbon-oxygen double bond, and so that will show in the typical region that we would expect. And so that's the answer to chapter 21, problem number 80.